Hello everyone. This is week 8, and we will try to solve two-dimensional heat conduction problem while taking the triangular element and rectangular element, and also we will solve assignment 8 problem. So let's see. So before moving to this problem, let's revise some fundamentals, then we will start it. So, this is a 2D heat conduction problem. So in the previous class, we already saw that the variational statement for the heat conduction problem is given as below. Okay, so we already saw in the previous lecture that the major problem to solve the FEA problem is to integrate the whole domain. Like if you have some this kind of body, two-dimensional body, and we have this kind of meshing, then there is a problem to do the integration, because if you have some regular body, if you have some rectangle, or if you have some triangle, where we already know what is the equation of edges, then it is easy to integrate. But when I talk about the regular body, then it's not easy to integrate. Okay, because if the integrand is a function of x and y, then it's not easy to integrate, because we don't know what is the, like if I take this kind of triangle, and if this is a kind of element, then to integrate we need to know what is the lower limit of x and what is the upper limit of y. Similarly, what is the so suppose we are taking, first we will integrate y. So we don't know what is the lower limit of y, what is the upper limit of y, and similarly what is the lower limit and what is the upper limit of x. because this is a very arbitrary triangle and it is not easy to integrate. But if you take a domain, if you take a square plate or rectangular plate, then we already know the what is the boundary and what is the equation of this boundary, then it is easy to integrate, and we already saw this thing in the previous lecture and previous assignment. But in this week we will try to solve such problem where the domain is very irregular but the meshing is triangular, and the physical domain of the triangle is something like this, and we want to convert this kind of physical domain into the master domain where we will see that on the x-axis it will be a xi, and on the y-axis it will be a eta. And then if we are able to convert from the physical domain to the master domain, then this integration will be very easy, because in this case the integral will be something like this. Suppose the coordinate, in the master domain, suppose the coordinate of this triangle is 0 0 and this one is 1 0 and this one is 0 1, then it is easy, because on the y-axis we can see that eta is varying from 0 to 1, and from the x-axis which is nothing but the xi, and xi is varying from 0 to 1 minus eta. And suppose it is a function, if we are able to convert the whole integrand as a function of eta and xi, then we can easily integrate this, because all kind of triangle can be converted into the master domain. So that's why we need to convert this whole integration, the double integration, and it is a line integration, whole double integration in terms of zeta and eta, in terms of xi and eta, and where eta vary from 0 to 1 and xi is also vary from 0 to 1. Similarly, we can also convert this domain into a rectangular mesh. If we are able to convert the whole domain into a rectangular mesh, then in this case, if this is a physical domain and if you take this element, suppose this element is something like this, and if we are able to convert this into a square which is a master domain, and it can be converted into a square, and here there is no such problem like this. Here we can directly integrate from 0 to 1 and 0 to 1 if we are able to convert the integrand as a function of xi and eta. So the main point is how we can convert or how we can change the variable so that we can convert the physical domain. We can convert the physical domain into master domain. So this is the challenge part of this is the main objective of this lecture. So let's see how we can do it. So previously we saw that if we have some element, triangular element in the physical domain, and if suppose if this is node 1, node 2 and node 3, then the temperature of this element we can write as U1 phi E1 plus U2 phi E2 plus U3 phi E3. Okay, and we can see that this phi 1, phi 2 and phi 3 has to be adjusted such that when the value when we substitute the coordinate of node 2, then the value of phi 1 e should be 1 and other phi 2 and phi 3 should be 0. So suppose the coordinate of this node 1 is x1 y1 and this one is x2 y2 and this one is x3 y3, then we can write for element 1 phi 1 for this particular element. Then when we substitute it, and here I forward that if I am assuming that this phi 1, phi 2, phi 3 is a kind of linear element, linear two-dimensional shape function if I am considering, because we have to consider it. Okay, okay, so we already saw that this phi 1, phi 2, phi 3 has to be such that when you substitute node 2 and node 3 coordinate, it should be 0 for phi 1 and other phi 2 and phi 3 should be 1. So in the previous lecture we saw that we can directly write like this when you substitute, and we can see that we have how many equations? We have total 9 equations. Okay, 9 equations and 9 variables. So if we convert it into a matrix, then we can write 1 x1 y1 1 x2 y2 1 x3 y3, and here it should be a1 a1 b1 c1 a2 b2 c2 and a3 b3 c3, and here it is a identity matrix. And if I want to get this matrix, which means that I am assuming that this matrix is A, then it is nothing but X transpose. If it is a X, then not X transpose, X inverse. Okay, so we can easily get the value of this coefficients by finding the inverse of this matrix. Okay, so this was the all about the previous lecture, and then we could easily convert. After doing all this, we can convert Kij like this. Okay, so this is the case when we already know what is the edge equation, and you can say that when we it is easy to do the double integral, but what will happen when the integration is not easy, because we don't know what is the edge what is the equation of the edges. So in that case, what we will do is we will convert the physical domain into the master domain. Okay, so for that what we will do is, let's convert the physical domain into the master domain. Okay, so in this case what we will do, suppose this is the physical domain and this is the master domain. Suppose the equation node point is 1, 2, 3, and here 1, 2, 3. This is the element E and this is the element T. So it should be a mapping. Okay, a mapping should be such that, suppose that this coordinate is x1 y1 and this coordinate is x2 y2 and this coordinate is x3 y3. Okay, and what I want to know is, I want to write x such that it should be a function of x1 n1 x2 n2 plus x3 n3. Okay, and similarly I want to write y equal to y1 y1 n1 y2 n2 plus y3 n3. Okay, and here n1 n2 n3 should be adjusted such that this is the master domain, and in the on the x-axis I am assuming it should be a xi and here it should be a eta. Okay, and what I want to know is, when I put x equal to x1, okay, and y equal to y1, when I put x equal to x1, y equal to y1, then Xi should be equal to 0 and eta should also be equal to 0. Okay, so then what we will do? Suppose I'm assuming like that. Suppose n1 I'm assuming is a plus a1 plus b1. Suppose I'm assuming that a1 plus b1 plus xi plus c1 eta. Okay, and similarly like n2 equal to a2 plus b1 xi, sorry, b2 xi plus c2 eta, and n3 I'm assuming that a3 plus b3 xi plus c3 eta. Okay, and when I substitute everything here, then after solving, like this is the first condition, and similarly if I talk about the second condition, it should be when I want to write here, this is the first equation, first condition, and second condition is if x equal to x2 and y equal to y2, then xi should be equal to 1 and eta should be equal to 0. Similarly, when x equal to x3 and y equal to y3, then zeta must be equal to 0 and eta must becomes 1. So when you substitute everything, when you substitute the condition 1, 2 and 3, when you substitute 1, 2 and 3, and you will get I'm assuming that it should be hat, because it is a different from the normal shape function, because on the previous shape function it depends on the physical domain, but here n1, n2, n3 depends on the master domain, so that's why I'm using hat in this case. Okay, so now, so after solving equation 1, 2, 3, we will see that we can easily get n1 hat is 1 minus xi minus eta, n2 hat equal to xi and n3 hat equal to eta. We can clearly verify our solution, like when you substitute here, when you substitute xi equal to 0, 0, then clearly n1 becomes 1 and all other shape function become 0, so we can clearly see that x becomes x1 and y becomes y1. Okay, so this is the solution. So this is the shape function we have to use, and this is a linear shape function. Okay, so we already saw that there are many different kind of polynomial or bilinear kind of shape function, and we already saw that we can easily construct a different kind of shape function by using the Pascal's triangle also. Okay, so depending on the complexity of the problem, we can easily construct, or we can easily get the different kind of shape function. But here it is a linear, shape function, because in this case we already saw that we can there are two types of problems, that is H type FEA and P type FEA. Okay, when we are keeping the shape function as simple as and as simple, very simple, then we have to increase the number of elements. Okay, so in that case we can say that it is a H type. But when we increase the order of the polynomial of the shape function, then we need very less number of elements. So will in that case we can say that if a problem is P type. So here we can I mean just a very simple thing we are doing here. So we are considering the linear shape function. Okay, now the major thing is, here we already know that what is n1 n2 n3, and we can easily write x as xe1 1 minus xi eta plus x2e xi plus x3e eta, and similarly y equal to y1e 1 minus xi minus eta plus y2 should be y2 y2e xi plus y3e eta. Okay, so yeah, while doing the double integral, so we need to convert the variable from the master domain, from physical domain to master domain. So first we need to convert dx into dy as d xi del eta, and from the previous class we already saw that the Jacobian, the determinant of the Jacobian can easily do that, which means that dx dy can be written Jacobian, and we already know that Jacobian should be always greater than 0, otherwise it is not possible. Okay, so I mean there is no need to write the modulus or no need to write the determinant of j, it is always positive if we are taking the proper meshing. Okay, so dx dy can be written as d xi d eta. Okay, and or you can also say that if I want to write dx, okay, because there is also a need to change dx into a d zeta and d xi and d eta. So in that case dx can be written as dx divided by d xi d zeta, d xi, dx divided by d eta d eta, and similarly dy can also be written as dy by d xi sorry, yeah, it should be partial derivative, should be written as del y, yeah. So del y by del eta d eta, and in the matrix form I can write dx dy, and this one is dx by del x by del xi, del x by del eta, del y by del xi, and del y by del eta multiply del xi, del dxi and del eta, and this is called Jacobian. Okay, this is called Jacobian. But the main thing is we don't need this. What we need is we want to get d xi d eta after converting dx dy. Okay, what we need is we want to convert dx dy vector into d xi d eta, and it's a very straightforward thing. We have to do simply as inverse of the Jacobian matrix. When you do it, we can easily convert this thing. Okay, and why we need this? Because in the stiffness matrix, which is Kij was the double integral, or we can say single area integral, that was lambda naught and n ix n iy plus n njx n iy and n jy d. Okay, and this is what nix njx is nothing but this is del ni by del x del n j by del x plus del n I by del y del n j by del y, and it is nothing but the gradient of ni, gradient of nj, gradient of ni dot gradient of nj. This is nothing but the gradient of ni, gradient of nj. But what we need is, we want to convert this thing into del ni by del xi del nj by del eta. Okay, then we can easily write the stiffness matrix. Then what we will do in that case? What we will do is, if I want to get del ni by del xi, then what we will do is del ni by del x by del xi plus del ni by del y and del y by del xi. Okay, similarly, and we can also if I want to write independent of this, yeah, I mean it's fine. Okay, and similarly a del ni by del eta, I have to write del n by del x by del eta plus del ni by del y by del eta. Okay, and these two equation can be written in the matrix form. These two equations can be written in a matrix form is like this. We can write these two equations in the matrix form, and we can clearly see that this is nothing but del x by del zeta, del y by del zeta, del x by del eta, and del y by del theta. Okay. And this is the thing. But what we need is, we want to convert, we want to write this into this form, which means that what I want is del ni by del x, del ni by del y into del ni by del xi, del ni by del eta. And when you do that, then you have to write, because it is as usual, we already talk about that, this is Jacobian, and this is nothing but the Jacobian inverse. Okay. Now we arrived what we want. Okay. So which means that del n I dot del n j can be written as, okay, this is what, this is nothing but del ni, this is del ni, del ni, okay, and this is what, del bar ni, which means that I want to partially integrate, partially differentiate with respect to xi and eta. So what we can write is del ni equal to j inverse times del ni. I will write clearly, which means that I can convert del ni equal to j inverse del bar ni. So you can write like j inverse del bar ni, okay, dot j inverse del bar nj. Okay. And if I want to write in the matrix form, then what I can write? I can write bar ni transpose j inverse transpose, okay, and j inverse del bar nj, okay, or del bar ni transpose into j inverse transpose j inverse and del bar nj. Okay. So this is the matrix, this is the matrix which we have to write. Okay. And this is the Kij, I mean if I want to integrate, this is the integrand. Okay, this is the integrand of index ij. Similarly, if I want to get g times n ni dA, that is very simple. I can write ni is already in the xi and eta, and at the place of dA I have to write j del xi del eta. Okay. Now the major challenge, now the biggest challenge is to do the line integral of q n ds. Okay, what we will do for this thing. Okay, so let's explain this, what we will do for this. Okay, suppose we have a triangle. Okay, and in this case what we will do, In this case, first we will directly convert. First we will write k, I mean q, as a function of xi and eta. Okay, and n is already as a function of xi and eta. But the main thing is how we will convert ds. How we will convert, I mean what should come here so that ds becomes either del xi or del eta. Okay, what we will do here in this thing. Okay, so here it will be ni. Okay, yeah, so let's do this. Suppose what we have to do is 0, I mean o, a and b, and in the whole domain we have to integrate. Okay, suppose in this domain it is a q1 heat flux, q2 heat flux and q3 heat flux. Okay, so what we have to do is we have to integrate OA to the whole integral minus AB to the whole integral, okay, plus minus BO whole integral. Okay, and what should be here? Here you can see that whatever the variation is, what we have to do is it will be always a function of xi. It will be always a function of xi, and it will vary from 0 to 1. It will vary from, not 0 to 1, minus 1 to 1. And what we will do, what we have to do is we have to write eta. We have to write eta equal to 0. Whatever the integrand, first we need to convert that integrand as eta equal to 0. Okay, and then whole integrand will become a function of xi. Okay, and then in the master domain this xi will be integrated from -1 to 1. Okay, similarly while integrating on the line AB, it will be also varying from -1 to 1, or suppose, yeah, let's check what will happen with AB. Okay, what will happen with AB? Because we have to convert ds into either del xi or del eta. So what we will do is ds can be written as dx square plus dy square. Okay, and dx and dy can also be written as dx by del xi raised to the power 2 plus dy by del xi raised to the power 2 and del xi. Okay, in that case, and we already know that what I have to write, x equal to x1 n1 plus x2 n2. Okay, and y equal to x1 n1 plus y should be y1 n1 and y2 n2. And when you differentiate it and when you substitute here, it becomes, you can see that del x by del it becomes x2 minus x1 by 2 raised to the power 2 plus y2 minus y1 by 2 raised to the power 2 and del xi, and it becomes 1 by 2 1 by 2, and this is nothing but the length of this line. Suppose this is the AB, so AB, this become H AB, and now simply del xi, ds becomes del xi. Okay, now we can easily convert. Okay, now we can easily write whatever the equation is. Simply we have to integrate from -1 to 1. Okay, and we have to do everything here. Okay, so let's take one example in this case. Okay, so this is the assignment which we have given. Let's take 2-minute break and we will see this assignment. Okay, so let's solve this assignment problem, which is assignment 8. This is assignment 8. Okay, so let's go to the MATLAB. First let's read this problem. It is saying there is a steady state heat conduction problem for the finite element mesh consisting of a triangular square element, triangular and square. There are two elements. Okay, one is the square element, and another is a triangular element. Okay, and here the coordinate is 0 0 2 0 2 2 and 0 2, and here the coordinate is 2 0 4 0 and 2 2. Okay, and this is the element number 1 and this is the element number 2, and it is also given a global node and local node. Okay, so the global node is already given and local node is also given, so let's write it. 1 2 3 4 and 1 2 and 3. Okay, and it is given that Qn, and Qn is what? 10 root 2 watt per meter, and for element 1 it is given as 1 watt per degree centigrade. K2 thermal conductivity 2 watt per degree centigrade, and there is a heat generation that is 20 watt per meter square. Okay, and there is a constant wall temperature which is at node 1 and node 5. So T1 equal to 0 degree centigrade, T5 is also 0 degree centigrade. So this is the all data which we have given. Okay, so let's go to the MATLAB and we will see. So yeah, so we can see that there are 5 nodes, so that's why I have written a nodes equal to 5, and I am assuming x and y as a symbolic variable, and k global should be 5 by 5. Yeah, so because there are n nodes, so that's why it should be T1, T2, T3, T4 and T5, and I am assuming third degree of polynomial for the Gaussian quadrature. So this is the order of the Gaussian quadrature. Order of Gaussian quadrature. And the thermal conductivity for element 1 is given 1, and for element 2 is 2, and there is a heat generation, and heat generation is only, you can see that the heat generation is only in the square element for element 1 only. So that's why I am assuming for the element 1 there is a heat generation 20 and 0 for element 2, and there is a global node. So I am assuming for element 1 the global node is 1, 2, 4, 5. Okay, and for element 2 it is 2, 3, 4. And for what is the local node for element 1? So 1, 2, 3, 4 and 1, 2, 3. Why I am doing this? Because when you write when you write the k local, and when you merge the k local with the k global, then this indices should be matching, otherwise the k local will be filled in another location in the k global. So that's why I have to do this. Okay, and here the edge matrix, I will tell you, I will also show what is the main role of the edge matrix, why we are doing this. Because when you mess with the huge number of elements, suppose there is some kind of messing is like this. Then you can see that it is very difficult. Suppose now let's find the shape function for element 2. So here the n1 what it should be, it should be like when x equal to 4 and when y equal to 2 it should be 0. Okay, so if I write 1 by 2 and 4 minus x minus y, then we can clearly see that when x equal to 0, okay, when x equal to 0 and y equal to when x equal to 4 and y equal to 0, it should be 0, and when x equal to 2 and also y equal to 2, it should be 0. So similarly, what should be n2? N2 should be something like 1 by 2 x minus 2, okay, and also what it should be, n3 should be something like 1 by 2 y. And here it's not very difficult to find all these things, because we already know that what should be, suppose I want to write n1 as something like a1 plus b1 xi plus c1 eta, n2 equal to, I want to write a2 plus b2 xi plus c2 eta, n through n3 a3 plus b3 xi plus c3 eta. And if I want to get these coefficients, then it should be something like the matrix, the inverse of this matrix, okay, I mean A equal to inverse of this. And what should be x? X should be simply all coordinates like 1 2 0 for node 1, and what is the coordinate for node 2? 1 4 0. The first column should be, the entry of first column all should be 1, and what is the node? 1 2 2. Okay, let's take x inverse. Let's find the x inverse. What is the x inverse? X inverse should be 1 by determinant of x. This is x matrix, determinant of x, and what is the cofactors? Okay, cofactors of x. Okay, and also the coefficient should be the transpose of that. I mean, this is not exactly like this, it should be a transpose of that. Okay, so what is the determinant of x? When you find let's find the determinant. Okay, so determinant of x should be 1 times 8 minus 2 times. Okay, and when you skip the whole row and whole column, it will be 2. So 8 minus 4, it should be 4. So here it will be 4. Okay, and let's find the cofactors. So the cofactors 1 will be 4 to 8. Okay, 4 to 8, and this will be 0 when you take this. So whole row will be minus 2, and this will be 2 minus 4 will be minus 2. Okay, and here it should be, when you skip this whole row, whole column, so this will be minus 4, and here what it should be, 2. Okay, and here what it should be, when you remove this, all this 2 minus 2, it will be 0, and now this will be also 0, this will be also 0, this will be what, 4 minus 2, so it will be 2. Okay, so it will be 2 minus 1 by 2 minus 1 by 2 1 1 by 2 0 0 0 1 by 2. Okay, and I already told you that the coefficients of all will be the transpose of that. So what will be the A transpose? A transpose will be 2 1 0 is it matching? Yeah, 2 1 by 2 should be 1 by 2, right? Okay, yeah, I told you this is the cofactor. I mean, this is the adjoint. This is the right now. Yeah, it should be, I'm wrong here. it should be adjoint, and whatever we found out is cofactors of x. Okay, and what we need is, we need the adjoint. So what will be the adjoint? Adjoint will be the cofactor, I mean the transpose. Yeah. So this will be the this is just a cofactor, so it will be transpose. So 1 by 4, so it will be 8 minus 4, 0 minus 2 minus 2 minus 4, 2, 0 0 0 2. I mean, again what I have to do is, we have to just write like this. So it will be 2 minus 1 0 minus 1 by 2 1 by 2 0 minus 1 by 2 0 1 by 2. I'm going to take the transpose, it will become 2 minus 1 by 2 0, and this will be minus 1 by 2, and this will be minus 1 1 by 2 0 0 0 1 by 2. So here you can clearly see that this is exactly what it looks like. So when you want to get the shape function without doing the hit and trial, then you can easily find the shape function like this. Okay, so let's move to the MATLAB code. Okay, so this is the derivative, because we have to find that, and this is the Jacobian, and Jacobian is nothing but the derivative of n with respect to x. Okay, this is the Jacobian, but not only the Jacobian, we have to also find the derivative. Okay, so this is the derivative of that Jacobian. Okay, and this is the inverse, and when you do the directly, when you write here, then you can easily get del n eta. Okay, del n eta and del n xi. Okay, so then when you write everything here, then you can easily get, this is what thermal conductivity determinant J, and this is similarly the whole thing del n by del n del g del x, in terms of when you write here, then it will be converted into the xi and eta. Okay, and this whole thing is nothing but the, for the rectangle, this is the triangle. Okay, and let's move to the force matrix. Okay, and the first part is for the rectangle, and the second part is for the triangle. Okay, so for the rectangle, what it will take is, it will take Q1, Q2, Q3 and Q4 based on the Nyman edges. Okay, because here what we are doing is, we are first giving the Nyman boundary condition based on the edge matrix. Okay, so this is the Nyman edges, and based on that it will find n1, n2, n3. Okay, and here you can see that when you're trying to integrate this rectangle, then what we have to do is, for the first edge, now here you can see that it is doing the line integral. Okay, here in this case it is doing the line integral, and for the line integral you can see that n1 is nothing but the thing when y becomes 0. Okay, and n2 is the thing when x becomes 2. Okay, and similarly n3 is the thing when y becomes 2, and n4 when x becomes 0. Okay, because what we are doing is, we are doing the line integral. Okay, and on this line integral, what we are doing is, we are converting the whole integral into a function of xi. Okay, into a function of xi. So what we are doing is, we are converting the whole domain into the xi. Okay, now this is the integrand 1, integrand 2, integrand 3, integrand 4. I mean the 4 edges. Okay, so everything will be added up here. So here you can see that the first integral for this edge. Okay, and for this edge we are integrating x from 0 to 2, and for y y it should be 2 to 4. Okay, yeah, y, that is correct, 0 to 2. Okay, and x should be 2 to 0. Okay, from here, and y it should be what, 2 to 0. Okay, so here this is the thing. Now the heat generation part, where we have to directly multiply the heat generation with Ni. Here there is no problem because it will be directly integrate the thing and to directly do the double integration when x varies from 0 to 2. Here there is no problem because this is the rectangular element, so nothing we have to do. Now let's move to the triangular element. Okay, this is for the triangular element. So for the triangular element, it has 3 edges. Okay, so there are 3 Nyman edges, 1, 2 and 3. And for Nyman edge 1, what will be the shape function? For the other Nyman boundary 1, the shape function should be when y equal to 0. And for this n2, okay, this n2 should be something like when x varies. Here for this edge, what is x? X equal to 2. And what is the x here? Here x equal to 4 minus y. Okay, so that's why we are converting, we are doing the line integral. So for that, what we have to do is we need to look, let's see why we are doing it. So to do the integration on this edge, okay, so what is the integration? Integration is q n ds. Okay, so for this edge, for the edge number, what is the nodal point? 2, 3. Okay, let's see for 2, 3 point, 2 and 3. So 2 and 3. So here ds should be what? Ds should be dx by del xi raised to the power 2. Or you can clearly, nothing to worry about that. You can also do something like directly integrate. We can also integrate directly, like ds. If I want to convert the whole thing as like this, suppose I want to write dx not in terms of xi. Let's see, dx square and dy square. What I want to do is I want to convert this whole integral in terms of single variable. Okay, so let's see. So we and what is the equation of this line? Equation of this line is x equal to 4 minus y, or we can also write y equal to 4 minus x. So let's see, like I want to write like dx is as it is plus dy. Dy is what? When you differentiate y, so it becomes minus dx raised to the power 2, and it will become dx root 2. So this whole integral becomes q n, and dx will become what? Sorry, it will be ds. Yeah, this whole term, there will be a vacant space here. Okay, and the whole term will become root 2 times dx. Okay, and here also we need to change, like q, if it is a function of x and y, then nothing to worry about that. But if it is a function of q is a function of x and y, then what we have to write? We need to convert y equal to 4 minus x. Okay, we need to convert, if it is a function of x and y, then y we need to convert 4 minus x. And similarly n also we need to convert y equal to 4 minus x. Okay, for this particular edge, then we can directly integrate it. Okay, so let's see. So here you can clearly see that what we have done is, so here you can see that I have converted x equal to 4 minus y, and I have multiplied square root 2 and integrand. What is the integrand? Integrand is q times n2. And what is n2? N2 I have converted x equal to 4 minus y. So that's why it will give something like this. And here there is no issue in the heat generation part. So this is all about the force matrix. Let's move to the assignment. So let's run this code. So when I run it, I get k local ei. Okay, so this is the k local ei, and let's print this. It will be printed here. And what is the k local e2? This is the k local e2. And this will be a force matrix. And let's solve all this. And also we need to set the boundary conditions. So let's set the boundary condition also. What is the boundary condition? Boundary condition is the temperature on point node 1 and node 5 should be 0. So that's why the fixed node should be 0, and then it will be find all this temperature. So let's continue this code. Okay, so this is the solution. So in your problem it is saying what is the K22. So K22, so this is the, I have not printed the global stiffness matrix. So let's print that global stiffness matrix. Okay, let's print the global, global, I think global temperature is already printed here. Okay, so let's run this again. So this is the global stiffness matrix. Okay, so what it is asking, what is the K22? K22 is 2.6. I mean it is you can check this whatever it is. So this is the solution. So let's check, if it is given the problem, what is the solution? It is saying what is the K22. So K22, if I talk about the K22, so where it is K22? So K22 is here. So it will be a sum of K22 of element 1 and K11 of the element 2. So that's why it is the answer. And let's see, it's all about, you can do it. What is the N1 and 2? It's all have been solved. Let's go, element 1. Let's go to the element 1, stiffness matrix 1. Element 1, it is saying what will be the K22. So 0.666, that is 2 by 3. And element 1, what will be the K23? So minus 1.6, that will be minus 1 by 6. What will be K33 of element 1? So it will be 0.666, that will be 2 by 3. So what will be the for element 2? Let's go to the element 2. This is the element 2. So it is asking what is 1 1. So it will be 2. What will be 1 2? It will be 1. Minus 1. What will be 1 3? It will be minus 1. What will be the 2 2? It will be 1. What will be 2 3? It will be 0. What will be 3 3? 1. For heat flux of the rectangular element, what is asking? 1. So it will be 20. What will be 3? It will be also what 20. For element 2, what will be 2? So that will be, for 2, what is the 1? So that will be 0. What will be 2? That will be minus 20. What will be 3? It will be also minus 20. And it is asking what is the value of temperature at the midpoint of AB. Okay, what is the temperature? It is the midpoint of AB. So midpoint of AB, which means that is the node 2. Okay, so let's see what is the temperature at the node 2. It is the 0. It should be 0. The answer should be 0. So 0. Now it is asking the value of temperature at point B. So what is that point B? B, which means node 3. Node 3 is minus 20. So that will be minus 20. It is asking what is the value of temperature at point 4. I mean 4. So what is the, so that is 0. So that is, this is the 0. So this is all about the solution. Now let's move to one problem where we can see, we can solve not only the triangular element but also with the rectangular element. So this is all about the assignment problem. Now let's solve one problem. So yeah, so the problem is, there is a square plate. There is a square plate and the length of the plates are 2 units. The dimension are 2 units. Okay, and this one is the adiabatic wall, and Qn equal to 0 here, Qn equal to 0 here also, Qn equal to 0 here, and this is the temperature of this wall. There is a temperature of the wall, that is T0 equal to 100 degree centigrade. Okay, and it is saying that heat conduction is 25. The value of heat conduction is 25, and also there is a heat generation, that is G equal to 1000 watt per meter cube, and here it is what, Kelvin. I don't know the dimension. Let's see what was the dimension of that. Watt per Celsius. Okay. So it will be watt per Celsius. Okay. So let's solve this problem. And we can solve this problem by discretizing this domain by meshing as a triangular element and also with the rectangular element. Okay, so let's take it as a node 1, 2, 3, 4 and 5, and similarly 1, 2, 3, 4, and let's discretize here as a rectangular element as node 5 here. Okay, and the local nodes are suppose 1, 2, 3, 1, 2, 3, 1, 2, 3 and 1, 2 and 3. Okay, and here 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3 and 4. Okay, so yeah, so this is the case, and let's solve this problem. With the triangular element method. Okay. So first we need to see what is the connectivity. Okay. So for element 1, suppose this is the element 1, element 2, element 3, element 4. Okay. So for element 1, what is the connectivity? 1, 2. This is a global connectivity. Okay. So 1, 2 and 5. So this is 2, 3 and 5. 2, 3 and 5. And this is 3, 4 and 5. And this is 4, 1 and 5. Okay. And what are the nodal coordinates? Nodal coordinates are 0, 0, 2, 0, 2, 2, 0, 2, 1, 1. Okay. And Neumann edges, we need to also see the Neumann edges. So there are 4 elements, so we can also see that there is no such heat flux. So that's why for each element we can see that there are 3 edges. Okay, so based on that, okay, and there is one more thing we need to very take care of, like we are very concerned about the ordering of these local nodes. Okay, so you can see that first what I am doing is I am taking the left corner as the first node, right corner as the second node, and the top corner as a third node. Okay, and based on this only the Neumann edges have been written. Okay, otherwise there will be a problem in doing the line integral. So that's why the nomenclature, I mean the naming of these nodes is very important. Okay, otherwise we will get wrong answer. Okay, so Neumann edges, I mean there is no such heat flux, so that's why all the values will be 0. And this is the global nodes, I mean these are all same. Let's move to the force, I mean the stiffness matrix. Okay, what I have done in the stiffness matrix. Okay, so these are all same. And also what I'm doing here is, if I am taking the triangular, nodes, I mean the triangular element. So suppose this first element, the first element is something like this. So 1, 2 and 3, and since this is in the physical domain, it will be converted into the master domain. And this is physical domain. Okay, and in the master domain we already saw that the x-axis will be xi and y-axis will be eta, and the coordinates will be 0, 0, 1, 0 and 0, 1. Okay, and also when you do the double integration, then what we have to do is we have to do like this. I mean xi equal to 0 to xi equal to 1 minus eta, and eta should vary from 0 to 1, and this will be del xi del eta. Okay, but since I mean every time we have to do this integration for the double integral. Okay, but the thing is, for every triangular element we have to do the same integration. Okay, but we have one very advantageous thing is, when you do the Gaussian quadrature, then for this particular integration also, I mean for every element we have to do only this kind of integration. Whatever the integrand is, we have to do only this kind of integration. And when you take the rectangular element, then what will be the form of the integration? That will be 0 to 1, 0 to 1. Okay, so in this case when you convert here, then we can see that in the Gaussian quadrature it is possible to do this kind of integration also, because there is a repetition. So we can also write the Gaussian quadrature for the right angle triangle, okay, for the triangular element. So for the 3 points, so this will be the weights and this will be the coordinates, okay. So we can directly use it. So in that case we don't need to to do the integration, this kind of thing. Only what we have to do is we need to convert the variable from from the physical domain to the master domain, okay. So yeah, so first what it will do, it will take xi eta value from the Gaussian quadrature 2D, and then it will find the Jacobian and then inverse Jacobian and the Jacobian inverse transpose, okay. Why we are doing this? Because we already saw that this thing, this thing, okay. So here you can see that what it is doing is, it is doing WQ lambda, okay. This is the weight, lambda is the thermal conductivity, this is the determinant of Jacobian. Now you can see that what it is doing is dx, I mean this is the vector, that is del ni, okay. So del ni, and then J inverse and J inverse transpose into transpose of that. And you can see that it is the opposite of that, because in the MATLAB this value is already saved, in the vector form. So that's why when you take the transpose, then it will become reverse of that. So that's why this is the integrand, okay, and then it will be added into that, okay. So this is the all about the stiffness matrix. Let's go to the force matrix, okay. This is the force matrix, and you can see that for the triangular element we need h1, h2 and h3. So this is the all about h1, h2, h3, and this is the shape function, and this is this is the heat generation part, and there is no such problem in the heat generation part. But the only problem was to do the integration on the right angle triangle, but we have already solved it, because the Gaussian quadrature can do that kind of integration also. So that is the thing. And this is the line integral, part. So here you can see that h1, h2 and h3, and in the line integral, since in the line integral we cannot use the Gaussian quadrature, because that is not a double integral, that is a single integral. But the single integral also, we can see that what we are doing is we have written xi to the xi and eta as 1 minus xi, okay. And then we can do it, because we already saw that, and that this will become a single integral and the whole thing will be integrated, okay. So let's run this code and we will see what we are getting it. So yeah, so for the triangular element we can see that this is the nodal temperature, so this is the nodal temperature 180 degree, and this is the fixed temperature, that was the wall temperature 100. And what is the temperature at node 5? This is the 153.33, okay. And this is solved by using the triangular element, okay. So you can see that there is some kind of line, okay, some kind of line is appearing here, okay, because there is no such values here, okay, it is absent. So what it is showing is it is some kind of plane, okay, but this is not a plane, okay. When you increase the number of elements, then it will be some kind of curvature, okay. So let's solve the same problem by using, okay, let's do one more thing. Let's change the denominators. So instead of 0 heat generation, let's make it as a 1. Suppose there was a 0 heat, what if q equal to 1, okay, on each edges. So suppose q equal to 1 here, q equal to 1 here, q equal to 1 here, then what will happen? Okay, so for element 1, what is the entry? Entry should be 1 0 0. Okay, because this is the edge number 1. For element 2, it should be 1 0 0. Okay, and there will be no such entry here. Okay, but for this there will be 1 0 0. Okay, so now let's run this code also and we will see the result. Okay, so here you can see that result has changed. No, what? Okay, let's run this again. Okay, result has not changed. Okay, maybe the temperature will be different here, but at the nodal point temperature will be same. I mean 180 degree, 180 degree, 100, but maybe on the wall temperature has changed. Okay, so let's go to the rectangular, and same problem we will do with the rectangular machine. Okay, so let's do this. So this is the x minimum. What I am doing is I will generate, because what I am doing is I want to increase the number of elements. Okay, suppose I want to increase the number of element as for this case, suppose I am taking three points here on the x-axis and 3 point here. I want to just verify the temperature. Okay, so in the case of rectangle, so here you can see that it is some kind of curvature. Okay, and what is the temperature here? So temperature here is 180, 180, 180, same as that, and here it is 160, but earlier it was 153.3. Earlier it was 153.3 degree. Okay, let's increase the number of nodes. If I want to know the information of this midpoint. Okay, so let's increase the number of elements. Okay, so how many points we need? 1 2 3 4 5. Let's increase to the 5. Okay, and here also let's increase to the 5. Okay, so what is the information about this? Here you can see that it is the curvature is becoming much smoother than previous. Okay, so let's see the temperature here. Here you can see that again it is 160 degree. Okay, so this is the difference. This is the difference of using a triangular element and a rectangular element. But again, this wall temperature are same everywhere. The wall temperatures are same. Okay, so you can increase, and also the result may change if we increase the heat generation and heat flux. Okay, so maybe the curvature will be something different from this. So this was all about the 2D heat conduction problem, and in the next week we will discuss the elasticity problem in 3-dimensional case, and we will refer the lecture which was uploaded on the NPTEL portal. Okay, so yeah, so see you.